And it's recording. All right, exercise 4C. So we're going to do 4C, 4D today. 4C, it's just you getting familiar with this notation. So P of X usually, you could use F of X, means exactly the same thing as function. But the reason why we use P is just to remind you it's polynomial, but you really don't have to use P. The rest of the other terms, you just got to be able to read that this just means the coefficient of x to the power of n, and we usually say that ax to the power of n is the, and I gave you a little hint on your notes, starting with LE. What do you think it could be, Samar? The leading term, that's correct. That is the leading term. And then n, which is the power over here, this is known as the, and I gave another hint, DE. Let's go with Leo. What's DE potentially? Degree or order. Very good. So it's degree or order. It's the highest power of your polynomial. So you've learnt in year 9, polynomial 1, which is linear. Then you were introduced to quadratics, polynomial 2, order 2, and then order 3 in year 11. Okay, and then you did a bit in quartics as well. So you did order 4. Now we're just saying that it could be to the power of 99. Okay, so we call all of those polynomials. So that hence this can keep going until it reaches A0, which is constant. Okay, there's a pattern to it. Now, as a reminder, we are revising cubic, so essentially you got to remember these two rules. I don't think they come up in your formula. Oh, sorry, this is my older notes. Yours one should be correct, but this should be difference of cubic factorization, and then this one should be sums of cubic factorization. So I'll write here sums of cubed, but your notes should be fixed. Let's see if you remember. So I gave a hint for the first one because that's easy to see. So x cubed minus a cubed, so difference of cubes, factorization. We see that if it's x minus a, then it's x minus a here as well. Notice that you have plus and a plus. Let's see if you remember then. What would the sum of cubes formula look like? Who wants to have a go? Hands up if you know. It's one of those formulas that could be useful in an exam, and I don't think they come up in your formula sheet, but it's just sort of a nifty thing if you pick it up while you're in an exam. So, anyone remember? X cubed plus a cubed could be factorized as, give you a template. There we go. Very similar to the first one. First brackets, let's go with, yeah, Luke? X plus a. Now the next part's the only one that I think usually is a bit trickier to remember. But one of the logics to it is every time you square a value, it's always going to be positive. So these two are always going to be positive. It's just a way to remember. It's not necessarily true. You can still have a negative in front of the a squared as well. Okay, so this is a plus a squared. So if this subtraction, and then the subtraction becomes plus, the only difference in this section is that it becomes minus ax. Okay, that's probably one way to help you remember it. So that's the only difference between them right there. But even if you didn't know, what's another way to do it? You can expand this times the positive and expand. You can test it and you will find out one of it will cancel out to that. If you've got a CAS, you can quickly do that in the exam. But it's just nice that if you know it, then if you notice it, you can factorize it quicker. Yeah? All right, so those are the only part of the notes. Otherwise, I asked you just then to do example 1. So here's example 1. P of x plus Q of x. So essentially you took this plus this, collect like terms, and you should get a quintic polynomial. This one just means sub 1 into P of x and sub 1 into Q of x and add them together. Should have been 15. Pretty straightforward. It's the next one that I want to do with you. All right, let's have a look at the next question. Example 2. So it is known that you've got x cubed minus x squared minus 6x minus 4, and then it factorizes nicely to x plus 1, x squared plus bx plus c for all values of x. So for certain values of b and c, they want you to now, first part A, expand and simplify this. Okay, because clearly unfortunately that's not a sums or difference of cubes at the moment, or we can't tell. and we're wanting to expand this. Why do we want to expand it? Because this is in expanded form. So this is called expanded form. Whilst this one is somewhat semi-factorized. Okay, so factorized form. See, because they're equal, that's important. The fact that you're saying that this side equals to the left side equals the right-hand side, if you have them both in the same form, meaning expanded form, or you could factorize this side as well, that's up to you. But what they're trying to get you to do here is make this an expanded form so that you can compare the terms. You compare the cubes with the cubes, the squares with the squares, and then you're able to then solve for B and C. That's the idea. Okay? So let's do a quick expansion here. So very simple idea. X times x squared gives you x cubed. X times bx gives you bx squared. And then x times c is plus cx. Then we've got 1 times x squared, so plus x squared. 1 times bx is plus bx. And then 1 times c is plus c. Cool, we've expanded. Now we need to simplify. How do we simplify this? How do we simplify this? That's going to be key in order to solve for B and C later. How do we solve this? I've expanded it. I've got my left-hand side, which I'm going to write over here. So my left-hand side is x cubed minus x squared minus 6x minus 4. Cool. So I've expanded the right. What was the point? So we've got to simplify it a bit further to make use of it. How would you simplify this? Let's go with Adonis. What do you think you would do? Equate the coefficients. Very good. So right now I can look at x cubed. And I look at this x cubed. Coefficient of x cubed at the moment is clearly 1. 1. So I can say, well, that's just 1 and 1. So it makes sense. But how do I do it for x squared? So this is x squared. This is x squared. But this is also x squared. What are you going to do? Yeah, that's pretty much it. The only, except for the A bit. What I would suggest for those who weren't sure here, I would actually factorize them. So I'd find the common factor. So right now I've only got one term of x squared over there. I've got two of them over here. So that means you can factorize them to simplify it, to make it smaller, which you were actually really close there. But if you had factorized these two terms, what do they both have in common? They both have an x squared. So if I take out the x squared, what goes inside the brackets? What goes inside the brackets if I took out x squared out of these two terms? Let's go with Krish. B plus 1. And then now this goes back to what Adonis was saying. This is the coefficient of x squared. We already know the coefficient of x cubed was 1, so you didn't have to do much about it. But the coefficient for x squared is here, and the coefficient for x squared over here is a minus 1. So therefore you could say the coefficients of x squared, if I equate them, since they're both equal, the negative 1, which is what Adonis was saying, is equal to not b plus a, but in this case it'll be b plus the coefficient here 1. So it'll be b plus 1. And you got yourself an equation to solve for b. Okay? And what is that? Was there any other x squares? No. So that means b must equal to negative 2. Okay, and then you do the same thing for the x's here. You can see the c plus b. Since they both have an x, that has an x, that has an x, you could have done the same thing again. Could have been plus c plus b x. You got a plus c there, but you can equate. But in fact, that last constant there, that's a c, and the constant over here is negative 4. So you don't really have to solve for c. You can just say c equals negative 4. Okay? Dude. Does that make sense so far? So that type of exercise, that's usually probably, I think there was one from your revision. If you did chapter 2, there might have been some of that, like expand and then equate. That's quite a common one. But all right, so now what we found is b is equal to negative 2, c equals negative 4. So that means our bracketed expansion, or factorization, is now x squared minus 2x minus 4. Let's move that over here. I already solved it for you. All right, so finding equation B and C, we've found equating coefficients, we've done that. So then we've factorized it to, all right, this last bit. What do they mean when they say products of three linear factors? What are they asking you to do here? Can I please have, let's go with Zach. What does it mean when they say, hence, write this expression, which is the initial question, as a product of three linear factors? What are they trying to say? Very good. Yeah, so what students may not realize is when you factorize, this is a factor. This is also a factor. They're both factors. But one is called a linear factor because that has only a linear equation there. This is called a quadratic factor. So when they say product of three linear factors, what they're saying is this is a linear times a quadratic. Turn it into three linear factors instead. But since that's linear already, you can't simplify that any further, so it must be x plus 1 here. You need to then factorize x squared minus 2x minus 4, which is what Zach was saying. Take the quadratic, break it into two linear factors. So factorizing x squared minus 2x minus 4, let's see if I can do that with cross method. Does it become just x and x, and is it just, well, can you do it? Maybe you have to do completing the square, do you? Is it 4 and 1? No. 2 and 2 doesn't work. Cross method doesn't work. All right, here we go. Let's revise your quadratic skills. So if you did cross method, finding the factors of the constant and the coefficient of x squared. If you can't make it work, what's another way? What other techniques can you use? Yes. You can complete the square. Quadratic formula. Those are the only two I can think of, really. So it's up to you which one you prefer. You can jump straight into it. Because they're asking for products of three linear, I wouldn't do quadratic formula because quadratic formula gives you the x-intercept, and then from the x-intercept, you have to rearrange everything to get the factor. I probably would have gone straight to complete the square. Okay? So here, I would have done, that's x squared. That's minus 2x. I've got a minus 4. In order to have a perfect square, that means half of this. So half of the x term, that's negative 1, and then square it. Half of negative 1, half of negative 2 is negative 1, square of negative 1 is plus 1. So I needed the last constant to be a plus 1, not a negative 4, to be a perfect square. This leaves me with x minus 1 all squared. So if you expanded that, that will give you that. And minus 1 minus 4, it's minus 5, right? Now, if you were to factorize this, so this is complete the square. What's the next step? This is revision of last year. How do I do this now? Let's go to Sarush. How do you factorize this? Because I've only completed the square, but I want it into linear factors. That was the goal, right? So what do I do next? What do I do next to break it into two linear factors? Say it again. There is x minus 1 in there, that's true. There is x minus 1 and x minus 1. Just a small detail. What skill are we using? Not sure. Jason? Yes. We have plus root 5, minus root 5. What is this hinting? That plus minus. What should that be hinting to you? Starting with D. Oh, good. I'm glad I'm actually stumping you here. That's a difference of perfect squares. So remember all of this is essentially saying I've got something squared minus something squared. A squared minus B squared is the same thing as A minus B times A plus B. Well, that's my A. Here's my A. That's my A term. And then to make 5 a squared term, it should be root 5. So using difference of perfect squares, I can say it's x minus 1, so that's my A plus B. And then A, again, minus b. Okay, that's just a quick revision. So from your last exercise, I think it's 4b, you probably might have something like that. But that's how you would do it if you would do it by hand, or for those who felt more comfortable, maybe you could have done quadratic formula and then reverse engineered it all. So if you moved everything from the right side to the left side, you would have got the same. Just got to be careful when you square root. It should be a plus minus. So then you have both answers. Okay? But that's how I would have done it. I would have just complete the square and then used difference perfect squares. Cool? All right, team. So that was 4C. That's, again, revision of how you would work with cubics, because in order to do cubics, your quadratics needs to be good. All right, let's move on to 4D now. 4D, team. 4D. All right. Let's do a bit of a theory revision. Cubics. Cubics has two main skills. Two main skills that you need to remember. And one links to this basic concept. 15 divided by 4. We know how to do this. How many 4s fit into 15? Can our players have... Let's go with Ewan. Ewan, how many 4 fits in 15 nicely? 3. Remainder? 3. This tells you the whole, but we call that the quotient. This is clearly the remainder. Anyone know what these two are called? They both start with D. I'm teaching my year 8s this too. Let's see. Does Ishan know? What's the numerator and denominator potentially called? They both start with D. So we know this is the quotient. That's the remainder. Does it? Oh yeah. Yeah, which one is it? It's dividend or is it divisor? Yeah, what's the top? Yeah, very good. Dividend, which makes sense, and divisor makes sense as well to help you remember. So those 4, this is your dividend, that's your divisor, that's the how many wholes you can get, and that's your remainder. Why am I sort of giving you this terminology? Is because of this. This is what students don't get. It was in your textbook last year, and it was trying to explain the remainder theorem. Most students skip that, memorize the remainder theorem, and they just go through believing it's true. But this is where the truth lies in how the theory comes about. Yeah, so it's understanding P of X is your polynomial, which is your dividend. And then you divide by, it could be a linear, could be a quadratic factor, we don't know. But we're dividing by a divisor. Okay? There would have to be a quotient. There must be something that fits in nicely, and then a remainder. But last year, in your exercise or textbook, they gave you this formula. They wrote P of X for a polynomial, where D of X, which is what you're dividing by, multiplied to Q of X, which is your quotient, what's left over, plus other X is your remainder. Now this is where that theory, if the divisor was X minus 1, that's why they said if you sub 1 in, okay, if you sub 1 in and the remainder, and whatever the answer is, that is your remainder. Have you noticed that if that was X minus 1, if I sub 1 in, that becomes 0. 0 times the quotient cancels out. And because you sub 1 in, it's R of 1. Whatever that remainder that had the 1 substituted, that's why they say when you sub 1 into the polynomial, so P of 1, whatever the answer is, that's your remainder. That's the remainder theorem. That's where they were showing it. And this whole thing was just based on the understanding of dividend, divisor, quotient, remainder. That's it. Yeah? If what I just said didn't make sense, who cares? Don't worry, I was just trying to alleviate that sort of memorization going on. But that's from last year, and this is the basis for remainder theorem. Okay? So, 2 skills I said that you need to know. Number 1, you need to know how to do long division with polynomials. Okay, so I'm going to do one with you to practice that skill from last year again. And then number 2, it's technically remainder theorem or factor theorem. Remainder / factor theorem. But there was an extra one which was called rational root theorem. For those who were very keen last year, you would have done, there was only one question for rational root theorem, but some people would have done it and they understood what it was actually about. And most people skipped it. They still don't know what it is. And that's what the next page I'll try to demystify for you. Okay? All right, let's do long division. So you need to know how to do it both on a CAS. This is how you do it on a CAS. I already gave you the sort of instructions. You can test it out on your CAS. The answer should be this. So let's do it by hand now and see if you get this. Okay? Here we go. So we are saying our dividend, which is the quadratic function or polynomial, divided by a linear. Okay? So we're saying, here's my divisor. How many of these x plus 2's fit into 2x to the power 4 minus 4x cubed minus 6x plus 6? Right? Let's see what you remember from last year. What's the first step? Can I please have... Let's go, Jacob. What do you do in the first step of polynomial division? Good. So 2x to the power 4 divided by x. 2x cubed. So we know that it fits in 2x cubes as a whole, but there's going to be a remainder. Because whilst this fits, the constant won't fit. So you got to think about, well, if I got 2x cubes of the x plus 2's, what you're really saying is this. 2x cubed of x plus 2. So when you expand it, you do get 2x to the power 4. Yes, that's what we wanted. It fits nicely. But then 2x cubed times 2 actually now gives you plus 4x cubed. So that. So when you find the difference to find the remainder, because you're trying to see how many times it fits in, well, yes, first term fits. Be careful the double negatives here. So negative 4 subtract 4x cubed is not 0. Negative 4 subtract 4 gives you negative 4 subtract 4. Negative 8, very good. So we got negative 8 x cubed. Drop down the next term, so minus 6x. And then you do the same process again. So before, Jacob said take the term and divide it by the first term. What we're going to do now is we take the first term, which is here, negative 8x cubed, and you divide it by x. Same thing again. Let's go with and this time. What is negative? How many of these x plus 2's fit into negative 8x cubed? Or what do you do to get the next line? Very good. Negative 8x squared. Alternatively, you could just do negative 8x cubed divided by x. And that's how you get this next line. So hopefully by now you know negative 8 times that will give you the negative 8x cubed that you want. But don't forget, you still have negative 8x squared times the 2 minus 16x squared. And you are finding the difference again. Difference of a negative is the same thing as removing debt. So hence you're gaining. So negative 8 gain 8 gives you 0. Makes sense. Negative 6 subtract negative 16. Again, removing debt means you're gaining. So negative 6 plus 16 gives you positive. Actually, you can't subtract those two. Because one is an x and r. Oh, tricky. So in this case, that was positive 16 x squared, and you still have a negative 6x. For those, if they're not used to doing what I just did here, you could put a 0 x squared there just to keep the columns out, if you prefer. Okay, so if you preferred a neater way of doing it, I'll just show you what it might look like. You could do it like this, and you could add on 0x squared. If that helps you. Okay, so that means when you drop down to 0x squared, then you've got negative 8 times 2 is negative 16, so 0 minus negative 16 is how you get positive 16x squared. Then you drop this one down, minus 6x. Up to you. Same result, but if it helps you to keep yourself organized in the algorithm, that's another way of doing it. And then same thing, so I'm gonna speed up now, so I'm gonna say, what times x gives you 16x squared? We know that's plus 16x. 16x times x gives you 16x squared. So here we go. We follow on again. Plus 16x squared. Find the difference. 16x times 2 is plus 32. And this cancels out. Negative 6 minus 32 is now negative 38x. And then you drop down the last term, plus 6. And finally, something times x gives you negative 38x, and we can see it's negative 38. And negative 38 times 2, what's that? What's double of 38? 16, is it 76? I think so. Yes, negative 76. So your remainder is 6 minus, so plussing 76, so that's what, 80, 82? Yeah, 82. There you go, we've got a remainder of 82, which is exactly what they've got. They've got a remainder of 82. And we should have 2x cubed minus 8x squared plus 16x minus 38, and yes, we do. Okay, so that's a revision of last year's skill, chapter 6. It was one of the key sort of milestones when you sort of enter into methods. So if that was something you struggled, you must know they do like to chuck something like that in, one of them here and there, but they will assess that you know how to do that. Okay. All right. Let's flip over. So that's revision for last year. If you need to go back to your old textbook, you should. Let's flip over the page. All right. Let's fill in some theories. And then I'm just going to finish off with rational root theorem for those who didn't do those questions last year, just to answer what is rational root theorem used for. Okay? Here we go. Here's your polynomial. So you did 4C. You've learnt how to read this function. We know that remainder theorem, I just proved to you before, that if you sub A, so whatever that number is, P of A, that gives you the remainder. Great. If, however, the remainder has a 0, so fill this in, the remainder is 0, we call that factor theorem. Okay, so if it doesn't equal to 0, we call it remainder theorem. If it equals 0, we call it factor theorem. Why is it called factor theorem? Because that means x minus a is a factor of the polynomial. Great. The last bit is the one that students didn't understand from last year. Well, most of them anyway. Rational root theorem. Can I get a show of hands who feel confident that they know what rational root theorem is? Let's say 5 out of 10 at least. Good, we've got 1, 2. All right, good. So at least I'll clarify. Semi, yeah? Rational root theorem is kind of like your, here's a basic understanding of it. What are we trying to do at the end of the day? So you got P of X, and it's a cube, right? AX cubed plus BX squared plus CX plus D. This is what you learnt last year. What's the goal? This is your goal. You want to get 3 linear factors, right? The problem is that it's not always going to be something like x minus 1, x minus 2, x plus 3, and then you can say x-intercepts are 1, 2, and negative 3. Because reality is that the intercepts isn't always going to be an integer. Can't be a whole number all the time. What if it was a fraction? Say half. Now if it's a half, I could still have this minus 1. It's still a linear factor, but now there's a coefficient of 2. You see, with these 2, remainder theorem, factor theorem, there's a lot of belief that it is going to be a coefficient of 1 in front of x, and there's going to be a nice whole number. That's what they're assuming. But what if your x-intercept is not a nice whole number, which we've seen a lot, right? This is the theory to say, well, this could actually now tell me that x could equal to half if there's a coefficient. And likely the cubics that you get, what affects that 2? Like, how do you get this 2? If you have a 2 here, it comes from A. Yeah? Because if you expand them all, isn't it just 2x times x and then times x? That's how you get the first term, which is the leading term, right? So that means the coefficients of x here, or these linears, must be a factor of A. I'm going to say that again because that's the key part on the theory. So the theory is saying if you took the coefficient of the linear of these factors and you times them together, it must give you an, okay, the very first leading term, coefficient of a leading term. This is why they use it as beta. See right here, they're saying, if that's beta, whatever that number is, we know it has to be a prime factor of an. And an, if I just zoom out, an was this one. This is an. That's what they're trying to say. This must be a factor of that. True? Because if you expand it, it has to eventually times to get there. And therefore, the last one, what's the last one for? Well, the last one, that's a constant. But if you expand all the constants, it will be a factor of that constant, right? So why is this important? Because when you get a polynomial where I'd say like 12x cubed plus 6x squared minus, I don't know, 3x plus 1, I'm going to do a plus 1. See that 12? We can't always assume that it's going to be x, 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 and then, I don't know, minus 1, plus 1, and x, right? We can't assume it's always going to be a coefficient of 1 here. In order to get a 12, one of them likely will have to be either 12, or a 3, or a 2, or a 4, or a 1. But if that is true, that means you don't just get x could equal to 1 as an x-intercept. You might have a 2 here. 2 times 6 is 12, right? And that's a 1. So this one might have a nice integer intercept. Okay, it might have a nice integer intercept, but this one won't. This one will have now a combination of this factor divided by this factor. Because if I asked you to find the x-intercept for this one, you would say x equals 1 on 6. But how'd you do that? You move the constant across and divide it by 6. That's what this is doing. You see that? This is your constant. If I asked you to do bx plus alpha equals 0 using null factorial, and I said solve for x, you would have moved alpha across, and that's what you'd get. But this is clearly the factors of the constant, and this is the factors of the coefficient of the leading term. So what's the rational root theorem? You only use it when you do the factor theorem test and nothing equals 0. Like you've tested x equals 1, doesn't equal 0. You tested x equals negative 1, doesn't equal 0. You do 2, negative 2. All the whole numbers don't work. That means it must be a combination potentially with a rational, meaning fraction. That's what you haven't tested. So here's the problem that I gave here as an example. 12 is the coefficient of the leading term. 6 is the constant. So you got the factors 1, 2, 3, 6 for the constant. 12 has 1, 2, 3, 4, 6, 12. Here are your prime factors. You got 1, 2, 3, and technically you got 1, 2, 3 over here too. Okay? So out of these ones, you've now tested all the whole numbers. So alpha over beta, so 1 over 1, so 1 over 1, 2 over 2, 3 over 3. Those are all the factors that are integers, right? Or 3 over 1 or 2 over 1. So can you see the ones I'm showing here? All of these don't work. All of these do not have a 0 factor. So the remainder doesn't have 0. So then I try, well, what if I took 1 from here and I divide it by 2? That's what I'm doing. Instead of doing 3 divided by 1, 2 over 1, 1 over 1, because I'm assuming it's a whole number, what if it's not? What if it's a fraction? So now I have to try, well, it could be 1 over 2, 1 over 3. Could be, well, that's about it, yeah. So, well, actually 3 over 2, and I think that's about it. Oh, 2 over 3 as well, yeah? So here I've got 1 over 2 plus minus, and I tested it, and so it so happens I got the answer. But that's what rational root theorem is. It's giving you that extra test. Rather than always subbing in whole numbers, you then sub in fractional. But you have to understand, where does the fraction come from? This is probably why rational root theorem was the hardest to understand. Okay, so if you haven't practiced that from last year, there was only one question with maybe like 6 examples to try. This is another exercise for you to try to sort of understand the theory. It's to add on top of what you already know. Okay, so 2 skills that you take out from last year. Long division and how to find factors. The whole point is to factorize a cubic. Okay? I put my answers here for you, but hopefully you can see the trial and error that I'm showing, how I would have gone through it using rational root theorem to get to the answer. Okay, fill that in. And if you want to have a go, you can have a go with the challenge question on the back. There is a hint to it. If you don't know how to start, my hint is for the back, quadratics. That's my hint. If you can try to think of quadratics in some way, that's the hint for both the problems in the challenge section. If you want to know the answers, go into OneNote and just scroll down and you should be able to see the answers there. Okay? But I'll stop my video there just so that you can see the point of today's lesson. So 4C, language, and then 4D, revision of cubics from last year. All right, team, I'm going to stop there.